Recording in progress.
Okay, so let's continue where we left off last time. And we are in the middle of the vibrational partition function. So as you recall, we had obtained the function and then last employed it here to look at the distribution of occupied states. So we calculate the Boltzmann probability. And if you insert the expression we had obtained, you end up with this expression. And if you plot this P as a function of the levels, you see a rapid decay in this function, right? So the main conclusion from this was that unlike the rotational energy mode, for vibrations, we typically occupy rather the lower states predominantly. And the likelihood for higher states to contribute is much, much reduced. I would like, unless there are any questions regarding that, I'd like today to now move to the vibrations for polyatomic molecules. So molecules that happen to have more than 2 atoms, that seems to be a possibility. And so we would like to know how this applies in that case, okay? So that would be a subsection C, where we will discuss the polyatomic systems. And again, we will rely on this idea that we can assume independent normal modes. Now, you know already how many there are. Just as a refresher, your number of states, which is also sometimes called capital omega, corresponds, number of degrees of freedoms, not number of states, I'm sorry. Number of degrees of freedom is 3n minus 5 for linear systems and 3n minus 6 for nonlinear. Okay. And I repeat again, the characteristic vibrational temperature, capital theta, is h nu over kBt. But now you have for each mode, you have a vibrational temperature. So we should denote this with another index. Let's use J for the vibration J with its frequency, nu J. The wind. Now, thanks to this independency assumption here, we also write our vibrational total energy simply as a sum over our omega modes. Okay. And these are the vibrational eigenvalues or energies for each mode. Now, since we do that, we can nicely separate again our partition function in each of the different modes. Okay. So our Q dot of the vibration is a product over all the modes Qj for the vibration. Okay. Now, we know how the partition function for one, that's what we derived last time, for one oscillator looks like. Now we have omega oscillators. That is this product of e to the minus theta vibration j over 2t divided by 1 minus e to the minus theta vj over t. So this is pretty straightforward. Now, note that we have now the index running over the modes. And in each partition function, of course, we still run over the states. Okay. So you can think about a simple example like water. Where you can have three modes, right? So 3n minus 6 makes three modes. And if my head is the oxygen and these are the hydrogen atoms, this is one mode, this is the other mode, and then I also have this mode, right? These are my three modes. And in each one, you have a different curvature, right? So I have omega equals 3, right? And if my oxygen is here, my hydrogens are here. My first mode could be the vibration in the angle. My second mode could be the asymmetric stretch. And my third mode could be the symmetric stretch, right? Now, you know already from spectroscopy that for some spectroscopies, the dipole moment really matters hugely. In particular, there's one mode, right? When it's the symmetric stretch, your dipole moment would not change. While if it's asymmetric, it changes, right? So there can be excitations or states in the Hamiltonian which you can or you cannot observe depending on what the mode looks like, okay? So to have an idea of these modes is really very important to have a better understanding of what's really going on. And these modes are simply the eigenfunctions to the what's known the Hessian, right? So these modes are eigenfunctions of the Hessian. And the Hessian is the matrix. Anybody know what's the Hessian? Hands up. Yes, please. Oh, come again? That's correct. It's the second order derivatives of what? That's right. Each coordinates we are differentiating, but what are we differentiating? We're differentiating the energy, right? So it's the second order derivative of the energy. Now, remember, we are putting in this harmonic oscillator, right? You differentiate that twice, you get the curvature of your harmonic oscillator, right? That is actually the frequency, right? It's related to the frequency from Hooke's law, right? It's the force constant. So what you're getting out of this Hessian, once you diagonalize it, are these vibrational frequencies you would observe in your infrared spectrum, within the assumption that things are harmonic, that the harmonic oscillator is a good model of the bond, right? So yes, these are the second order derivatives. Right, and where x can be x and y and z. So I have three, right? And so this is a big matrix, right? 3n times 3n. And when you diagonalize it, you get the normal modes, which is really nice. So there is a matrix Q which will diagonalize my Hessian, which means I can write this as an eigenvalue problem, right? So that matrix Q is the set of eigenvectors all right, in which you get the diagonal version of the Hessian. And if you do that exercise for the water molecule, these eigenvectors Q are exactly these vibrations which you see up here, right? So for every atom in your system, you get a vector, x, y, z, that tells you where the atom is moving, right? And so when I do these little exercises with my arms, you're actually seeing eigenvectors, okay? Now, in front of these eigenvectors, we therefore have eigenvalues, right? So there will be an eigenvalue attached with each mode, and that corresponds to your frequency, is directly proportionate to your frequency, right? And those are the energies we are using here as eigenvalues for our vibrational partition function. And you know how the harmonic oscillator, the higher states, it's an equidistant. So any eigenvalues of any other higher states are simply multiples of the lowest one, right? So once you know the lowest, you immediately have the entire spectrum, up to a level where, of course, the harmonic approximation breaks down because your bond is actually, or the mode is softer than a quadratic parabola. Are there questions on this? These are, who has heard about this before? Nobody really? You a little bit? Yeah. So these are things you really only learn when you study chemistry, right? And physical chemistry, and it's more sophisticated, right? It's a little bit more sophisticated, but it's something to meditate about. It's very very useful. All right. So given all of that, right, we can then arrive. And we are not doing this here now, in the tutorial maybe, or in the exam, or the vibrational energy of the polyatomic system. You will find that this is, again, our number of molecules, right? So the number of systems times KB, sum over all my modes, theta Vj over 2 plus theta Vj e to the minus theta Vj over t divided by 1 minus e to the minus theta Vj over t. Okay. And similarly, you can show through differentiation once more that the heat capacity must be NKB sum over J theta Vj over T squared e to the minus theta Vj T now. If we make the heat capacity molar and we neglect the denominator, we have as a rule of thumb the ideal gas constant times the sum over all your modes, theta Vj over T squared e to the minus theta Vj over T. So these capital theta, these characteristic temperatures, these are things people measure in spectroscopy and report it. So for your favorite molecule you're studying, unless it's very exotic, if you find the spectroscopic tables for it, you will find the thetas. And you can use this formula and plug in those thetas to estimate the heat capacity of your molecule, right? Without any other measurements. Of course, you could also measure the heat capacity, right? But that's sort of cheating, right? And last week, if you don't have the spectroscopic table of your favorite molecule because nobody bothered to measure it yet, well, then you can use what you saw last week to actually calculate using density functional theory those eigenvalues, and with those the characteristic temperatures, right? That's what you have here. Okay. I wanted to show you an example for these numbers. Which is CO2. Or are there any questions at this point? No. Okay. So let's note down the mode, the frequency, and this is an inverse wave numbers. Right? This is a common measure. Now, with Planck's relation and knowing the speed of light, you can convert this to energy. So this is the inverse of the wavelength, right? 1 over lambda. Often in infrared spectra, you will see frequency reported in inverse wave numbers, so centimeter minus 1. Now, CO2 has three atoms, and so we observe 1, 2, and then there's a third, fourth mode, which corresponds to a bending mode. So we go away from linearity. And the frequency for this one is 670 in the inverse wave numbers. So it's a lower frequency mode, right? And in order to extend the bonds, you will need you encounter stiffer potential. So you have to apply more force, more energy, and we can characterize these modes. This top one is the asymmetric stretch. This one is the symmetric stretch. And this is a bending mode, which is twofold degenerate. Now, regarding the infrared Raman activity, the asymmetric stretch is infrared active and not Raman active. The symmetric stretch is not infrared active, but Raman. And the bending one is infrared active and not Raman. So this is determined by the dipole moment, right? Now, the characteristic temperature is 11.5 for the top one, 6.5 for the symmetric stretch, and 3.2 for the lowest one. And that is at 300 Kelvin. So these are things you could find in those measurements, right? Or from your DFT calculations. And then for these three modes, you will find in terms of heat capacity, in units of the ideal gas constant, 0.001, 0.06, and 0.5, or 0.4, 0.7, 0.9 at the temperature of 300 Kelvin or 1000 Kelvin. Yeah. For the entropy and units of the ideal gas law, you find 0 for the top one, 0.01 for the second one, and 0.2 for the third, or again 0.1, 0.5, or 1.1 at 300 Kelvin or 1000 Kelvin. Okay. So you see that the shallow modes can wallow up more entropy, right? They are more easily accessible, right? And they can wallow up more heat than the higher ones, which are the stiff ones. Right? So I believe I told you already that potatoes have a very high heat capacity. So this is soft organic matter with a lot of conformational degrees of freedom. Those are the soft modes. Right? You don't want to store heat in stretching covalent bonds. Right? That's going to be very difficult. Right? So the softer your modes, the easier it is. Now you have tons of degrees of freedoms in these proteins and a lot of these soft modes. So that explains this remarkable heat capacity. Now something more solid, like an inorganic crystal, a rock or so, will not have such modes, right? And will exhibit a much decreased heat capacity in comparison. Are there any questions? Okay. This now brings me to subchapter 4.5, which is the electronic partition function. Now, what you have to think about when discussing this energy mode is, again, a typical coordinate change. So I'm changing interatomic distances or geometries, and then the ground state is your typical binding curve. Which you would get from your electronic Schrödinger equation. So this is your electronic Hamiltonian, the electronic wave function, the electronic eigenvalues. Now I have many solutions again of eigenvalues and eigenfunctions. And what you typically see here is the ground state, the electronic ground state. Right? So all the rules you've learned about geometry, for instance, in terms of angles or the valence shell pair repulsion rules, they're all referring to electronic ground states. Okay. So, for instance, you should know that conjugated systems or double bonds take a planar arrangement in place in space, but that only holds for the ground state. As you go to the excited state, things look differently. And so here's a drawing of the excited state. Of course, you can have even higher lying excited states. Okay. Now, we've just discussed the vibrations and how they relate to infrared. Now, as you go to higher frequencies in the electromagnetic spectrum, you enter next the visual window, UV vis, and that's where the colors come from. Right? And so you can imagine that these sort of energy gaps are much larger than what you would have in your typical vibration. Now, just to exemplify the impact of which electronic wave function you're in, right, on these potential energy surfaces, consider this molecule here. Which I believe you would all agree with me should be planar. And I can now rotate the proton out of the plane onto the other side. Now, due to rotational symmetry, I believe you'd all agree that this kind of process would be a double well. And this is indeed the ground state energy as a function of the dihedral angle of this proton. And this is the energy. Okay. Now it turns out that the first excited state has its minimum exactly where you would encounter a barrier height as you come with the proton out of the dihedral. So these two dihedrals correspond to these two angles. And in the minimum, you would have something where your proton comes out of the surface. Right? And now it becomes obvious to you that as I go to the first excited state, what previously was a local maximum has become a local minimum. Right? And so these common rules we grew up with do not have to be taken with caution. Again, it depends on the state you're in. Now, the excitation energy are typically so large that a continuous integration over the entire spectrum, like we did it for the rotational and the vibrational partition function, is really, mathematically speaking, a bad idea, right? So large that continuous integration of partition function is a poor idea. Okay. And there's no closed form expression for a geometric series. So now you might be saddened and disappointed and believe that things are hopeless. But fortunately, we can simply truncate things after the ground state. The gap is so high, right? If you plug it into your Boltzmann probability, the probability of the next highest state will be very small. So we just truncate it, right? So that's the worst case outcome that can happen to you in physics, that you just say, I don't have a solution, I'll truncate after my first order term. Okay, so truncation due to desperation and we say our QE is simply, and we take here a factor in front for degeneracy, right? Your lowest state can be degenerate, times E to the minus beta E0. And that's your ground state electronic ground state energy. So truncated after ground state. So one thing one can do, and that is sort of reasonable, is to say our E0, we could calculate it, for instance, using DFT, or we take an internal energy that was measured for the ground state, and we divide it by Avogadro's number to get to the microscopic level, right? So for one particle, right? So this could be a good way to deal with this. And this is, I should also note an F here. One can obtain it from the formation energy. And this will then, using our expectation values for the molar average energy should be our molar electronic energy. And now I'm just using our formula, RT square derivative of logarithm QE with respect to temperature. And now thanks to our super simple form, our truncated form, I simply have the logarithm of my degeneracy minus delta FUE over RT. Right. So because I changed to molar, my NA here became the R. And so what this then becomes is, because I'm differentiating the logarithm, I'm differentiating 1 over t, I'll end up with RT square times delta F U0 RT square, and that's simply my delta F U0. Okay, so I've basically recovered what I've put in. So again, the formalism is consistent with between macroscopic and microscopic thermodynamics. We've reached a full hour now, unfortunately. I'd still like this week to finish the electronic partition function, and then hopefully next week we can finally tackle the question of the equilibrium constant. I'd like to thank you all for your attention.